Okay, so I guess we'll get started. Just want to remind everybody that this is being recorded. So if you don't mind, please mute your microphone and close your camera unless you're a speaker. And with that, let's get started. So so welcome to the Open Shading Language Virtual Town Hall. Here's our agenda for today. I'm Chris Kulla, and I'm going to be giving you our intro and a brief project status. Then Mitch from LAIKA is going to give us a lightning intro to writing OSL shaders, which is a preview of the course he'll be giving at SIGGRAPH. And finally, we have Akshay and Fran from Pixar, who are going to be telling us about OSL in RenderMan XPU. And of course, at the end, we'll have some time for Q&A. If you have questions, don't hesitate during the talk, don't hesitate to put them into the Q&A on Zoom, and we'll address them at the end. Okay, so let's get started. So what is Open Shading Language? It's a shading language, first and foremost, for artists to describe materials in modern production renderers. It's integrated into many popular renderers and DCCs, including the ones listed here, among several others, as well as in some proprietary production renderers that are used at large studios. And it's not just a specification of a shading language, it's actually an open source compiler and runtime that works on both CPUs and GPUs. A quick timeline of the project. It started all the way back in 2008 at Sony Imageworks. The goal was to add a shading language for their in-house renderer. And the OSL project was started with a design that would be good for path tracing and physically based methods that have since kind of become standard across the industry. And interestingly, the OSL project was designed to be open source from the very start. In fact, it was mostly developed completely in the open. We knew that there were other studios and renderer developers that were thinking along these lines, that were interested, and we thought that this would be a good opportunity for collaboration. In 2010, it was presented at SIGGRAPH. Around that time, the main backend for the engine was switched to LLVM. It started actually as an interpreter, but we quickly realized that LLVM was necessary to achieve really good performance. And it was in production use for a long time at Sony Imageworks. Since then, slowly other applications adopted it. And in 2017, it was recognized with Academy Scientific and Technical Award. And a few years later, in 2020, it joined the Academy Software Foundation. And this has been really great. It's provided kind of a neutral platform for engineers to discuss the project and coordinate their contributions moving forward. Here's the makeup of our technical steering committee. This is kind of a group of core contributors. We meet regularly and discuss what's next for the project and coordinate all the ongoing maintenance and development work. Now, I want to say a little bit about OSL as an open source project. Like, what is it made of? There's OSLC, which is our command line compiler, which is also available as a library, so it can be embedded in applications. There's a small library called OSL Query. This lets you do runtime inspection of compiled shaders. This is handy, for example, in a DCC if you want to be able to take a library of shaders and generate, for example, UI at runtime. You need to be able to inspect the shader, find out what kind of parameters it has, what are the metadata hints on these various parameters, and so on. Then the main workhorse of the library is libosl exec. That's our LLVM-based runtime. It handles both CPU and GPU. So we have a backend, the original one that works one point at a time. It's available on Intel and ARM architectures. We have a more sophisticated backend that's designed to shade multiple points at once. And this one can take advantage of SIMD instructions on x86 processors, for example, to shade 8 or even 16 points at a time. And then we have a backend for CUDA kernels. And this is where OSL will generate a kernel in PTX form. And then you can hand that to your NVIDIA GPU and run OSL shaders on the GPU. In addition to these core libraries, we have a number of testing applications. We have test shade, which is kind of a minimal example of shading a grid of points in order to produce an image. We have test render, which is a small minimalist kind of path tracer, really meant to showcase how do you build OSL into a renderer. So it's meant to be very small, but also give you kind of showcase kind of all the right API hooks of how a renderer would talk to OSL. And we have OSL Toy, which is basically just a small UI on top of Test Shade. It's kind of inspired by Shader Toy, and it's written in Qt, and you can use it for shader prototyping. What are some of the unique things about OSL compared to other shading languages? Shaders can be assembled into networks. Those shading networks are evaluated lazily. That means that any unused section of the network aren't actually evaluated. We also do a runtime optimization of the entire shader network. So we consider opportunities for optimization across nodes in the shading graph. And this is really designed to scale to very large production shaders, where shader writers typically assemble, or artists will typically assemble nodes that have lots of features in them. Not all of those features are being used. And that can leave a lot of instructions that don't actually do anything. And when we analyze the graph at runtime, we can detect those cases and remove, a lot of instructions from these cases. We've seen the optimizer remove upwards of 98% of instructions in kind of extreme cases. And this is definitely a key feature of the library and the runtime. Another cool thing is that OSL's runtime does automatic differentiation to keep track of filtering kernels, bump mapping, that sort of thing. It's much more accurate and more efficient than finite differences because it can work, inside loops, across conditionals. It can work through texture lookups, all of that. And another important feature that's related to the fact that OSL was really designed from the beginning to work for modern path tracers is that shaders return closures instead of colors. You can return colors if you want. Some people use OSL purely for pattern generation and only output colors. But if you want to use OSL for the whole material response as well, we have the concept of a closure, which lets the renderer decide how to integrate the lighting. The shader writer only needs to describe the intent of how the material responds to light, and then all the details of sampling and efficient integration are left up to the renderer. And the closure concept is very flexible, so closures can be nested, and that basically lets you do complex layering by basically building trees of closures. One question we get asked very often is, how is OSL related to Material X? Material X is kind of a higher level project, and it's really aimed at material interchange. So for example, the Material X library can convert material graphs into OSL code, but it can also target GLSL, HLSL, MDL, and other shading languages. But really, both projects work together to establish standards whenever we can. So for example, a few years ago, Material X adopted OSL's definition of noise functions. And in the other direction, OSL adopted Material X's definition of BSDFs and EDFs and layering operators, like I was just describing. We also have, through the test render program, we have a reference implementation of many of these Material X closures. So what's new in OSL this year? We released version 1.13 back in February, and since then we did about 10 point releases. The main things are we bumped, first of all, the minimum versions across our main dependencies. So that means Optics 7, OpenImageIO 2.4, iMath 2.4. These are kind of old, some of them, but we try to keep as much compatibility as possible by kind of surveying what people are using out there. We have initial support for the latest LVM. There's been numerous improvements to the NVPTX backend. That's for NVIDIA GPUs, like I mentioned earlier. This is pretty much production ready now. It's been shipping in a number of commercial products as well as internally in studios. We've extended the texture call to accept a color space keyword. So that gives renderers that support this the opportunity to do color space conversions and for shader writers to describe what they mean when they provide a texture. There's been a number of API changes for renderer integration. I won't go into all the details on this. We kind of covered some of these changes last year in our virtual town hall. But yeah. For shader writers, one change we made is rename what used to be called lock geom. It's a little piece of metadata you put on shader parameters. We now have split this into two keywords and kind of two orthogonal concepts. One is the interactive keyword, and the other is the interpolated keyword. And the intent here is to more accurately describe what the user wants. In the case of interactive, it's a signal to the runtime that this is a shader parameter that is going to be dialed interactively, and that tells the runtime optimization that it shouldn't be as aggressive in doing constant folding and all that because there might be a different value coming in later. And interpolated has a similar meaning in that it will tell the runtime optimization that it shouldn't optimize the value away, but it's for a different reason. It means that the shader should take into account the possibility this variable could come from a variable that's associated with the geometry, and therefore the renderer will insert a query to get the geometric parameter on every shade. Some other changes in OSL 1.13, we have a new journaling API for printing messages and errors. So this is, again, targeting people integrating OSL into their renderer. We've always supported the ability of shaders to print messages to the console, like for debugging or error reporting. But now these messages and errors are buffered in kind of a new API that's much more GPU friendly. We kind of accumulate all these messages during shader execution, and later we provide a way to query that buffer of messages so you can print them on the device, on the CPU side, as opposed to on the GPU, where that wouldn't be possible. And of course, there's a very long list of bug fixes that went into 1.13. And we typically try to keep up the current release 1.13 up to date with main in terms of any bug fixes that don't impact the API. Now, some highlights for later this year. We're hoping to release OSL 1.14. So in test render, we've added support for some new closures that came out of the work on OpenPBR under Material X project. So there's a new version of Oraneer and Sheen closures. For people integrating OSL into the renderers, we've continued the work on switching runtime strings over to UString hashes. So this impacts the shading system and render services API. If you're a renderer author, this is, again, we're continuing on making things more GPU friendly. And yeah, there's again a long list of small improvements to the optics CUDA backend. Like I said, it's already kind of in production use in several renderers now. It's working much better. On the build system front, in main, we've actually removed the boost dependency. So together with a similar change on the OpenImageIO side, this is one fewer dependency you have to worry about if you're integrating open shading language. We were using boost for just really a few things, and we kind of made the effort to replace that with more standard C++ constructs to just have one fewer library. Boost tends to be a kind of difficult dependency to wrangle sometimes. So this was nice to get off our plate. It'll be full LLVM 18 support. And we're also transitioning our documentation over to Read the Docs. This is a more modern web-based system for documentation. It's going to replace our old LaTeX written docs. Hopefully it'll make it easier for people to contribute and also to keep the documentation always up to date and in sync with main. Some things that are currently in progress. We're going to be raising the dependency minimums to align with VFX Platform 2022. We're not chasing the latest and greatest here because we like to keep the library as compatible as we can, but we feel like now's a good time to align with the version from a few years ago. So that means C++ 17, GCC 9, Python 3.7, IMath 3 and above. We may also bump the version for CMake and LVM, most likely just removing support for much older versions where we can. LVM is a project that moves relatively quickly, so if we support too many versions, it becomes kind of a burden on our testing matrix. The OpenImageIO project actually recently introduced a pretty cool feature that has the ability to automatically build dependencies through CMake, and it seems to have been pretty successful on the OpenImageIO side. So we're looking to port that over to OSL as well, where it makes sense. Obviously, there'll be continued GPU improvements since this is kind of one of the areas that a lot of renderer authors are working hard on these days. And I'll also call attention to some work that we're doing to improve guidelines on standard attributes and UI metadata. So you can take a look at our GitHub discussion page, but the goal here is to improve portability of OSL shaders across renderers. We have in some cases, renderer authors will expose kind of renderer-specific information with slightly different spellings from renderer to renderer. And we're trying to kind of bring that together, look at where things are shared kind of with just different spellings between renderers and come up with kind of a standard naming so that we can OSL shaders can just be that much more portable. Basically, most of the work here will be updating documentation, maybe implementing some of these suggestions in test shade and test render. We're looking to do the same for UI metadata. We've described some of the kind of standard metadata items in the documentation already. Things like this shader parameter should be displayed as a widget. This shader parameter has this value as the minimum and maximum. Those are kind of standard. We're looking to expand that to more sophisticated widgets for especially ramps. This is something that everybody tends to kind of reinvent, and we'd like to standardize that where possible. Some other updates that are coming down the pipe. Test render is, like I described, a kind of very minimal path tracer example. It currently operates on analytic spheres and rectangles. So this was done mainly just to keep the project as minimal as possible. If you've seen the small PT project, it's kind of in that vein. So there's no acceleration structure. We just assume the scene is very small. But many users were kind of requesting arbitrary model support, especially the folks on the MaterialX side would love to use test render as part of their unit tests, and they'd like to be able to use arbitrary models so that they can have kind of more interesting testing setups. So we did a prototype of this idea. It does mesh loading through a single file OBJ loader called Rapid OBJ. It's a very nice kind of small self-contained library. And all the rest we wrote ourselves. So there's a simple BVH implementation that's designed to be kind of very small. It's less than 300 lines of code. We're keeping the existing XML scene format for describing the shader networks and assigning materials. And for compatibility with what we had before, all the spheres and rectangle primitives will just be tessellated into triangle meshes. And with that, we have a system that actually passes the current test suite. But like I said, it lets us build much more interesting tests going forward. So here's kind of a teaser image here of the standard MaterialX shader ball with some basic OSL shaders assigned. Now, in parallel to this, Tim Grant from NVIDIA has done some work to port test render to the GPU. So this is also very exciting. It means we'll have an example in the repo of how to use the optics API in a real renderer. It'll also improve our ability to actually exercise the GPU backend in unit tests. of course, since we did this work in parallel, it'll take a bit of time for us to merge these two branches, but we're hoping to do this for the next release. Some remaining items kind of on our test render wish list. We'd love to support subsurface scattering, medium properties like scattering and absorption, and whichever else missing closures we have from the Material X and OpenPBR effort. I think there's just maybe 2 or 3 that are missing, but it would be good to have the kind of complete set. And also now that we have triangles, that would be an interesting thing to do there would be supporting displacement shaders. Again, just in the spirit of having something, a good example of how to do the basic integration of that into a renderer. I will say that it's important to remind everyone that non-goals as well as goals, we're not looking to make a production render here. We're not looking to implement the latest and greatest sampling techniques. We really want to focus on the project being easy to read and being a kind of a good example of what are the interesting bits of interfacing a renderer with OSL, not necessarily making a super sophisticated renderer. Beyond 1.14, as we look kind of further off into the future, we'll be continuing our transition from renderer services to free functions that are provided as LLVM bitcode. So this will improve optimization opportunities for LLVM. It'll make it easier to support the different types of backends that we have. And this is part of work that's ongoing by Intel to develop a SPIR-V backend, which will expand the existing CUDA backend to also support other GPUs, basically. It'll be an alternative backend, but the goal is to support GPUs from other vendors as well. We have some ideas in mind of evolutions to the language syntax, like new data types that would most closely match Material X, like having float 2s for UVs, RGBA colors natively supported, again, just for better alignment with Material X. Currently, this is supported by structs, but we think we do agree that it would be nice to support these natively in the language. Another feature we've discussed is the ability to reevaluate connected nodes in a material graph. This comes up in some cases, for example, when writing texture bombing shaders. If you want to keep that logic separate from the type of shader that's being scattered. Currently, this is actually difficult to do because the graph evaluation in OSL only evaluates a node once, so it's not possible to reevaluate upstream nodes with different parameters. We'd like to expose some sort of a way to do this, and this is something we've discussed at length in our meetings. Also on the list are some shader writer improvements, like named function call arguments similar to Python, or maybe templates for people writing libraries of OSL functions. And we also have a lot of work to do on our infrastructure. We have pretty robust CI for Linux and the CPU backends, but we still don't have great support for Windows and our GPU backends. And this is an area where we're definitely looking for help from contributors. Now, for those of you that came to the virtual town hall last year, you may notice that our roadmap actually looks slightly embarrassingly similar to last year's. The reality is a lot of our contributors are mainly focused on building their own products, and there's limited time to work on kind of future-looking aspects of OSL itself, especially those larger architectural changes and big features. We're chipping away at them, but they've been taking longer than we'd like. A lot of our time is focused on maintenance, bugs, CI, documentation, keeping all that up to date. So as a call to action, if your company relies on OSL, we can definitely use your help. No contribution is too small, so small fixes are really valuable. If you can help with documentation, CI, build, even just responding to issues on GitHub when people ask questions, tagging releases, that sort of thing. don't worry that you need to, be a lead developer working on, the large features right away. Even just helping with routine tasks would, help us to focus more effort on the bigger features. Of course, if you think you have some bandwidth to help us with some of these larger features, we'd welcome your help as well. And this is a good time to transition to talk about Dev Days. OSL will be participating in a Dev Days event this year. This will be in late September. And basically, it's a period of time where we'll be actively helping new contributors and encouraging them to join the project. All the members of the TSC will kind of be on hand to answer questions, review code, and yeah, to generally help you get started with contributing to the project. It doesn't have to be a code contribution. You can, help with documentation, help write unit tests. Again, no contribution is too small. We're just looking to help people join the project. So we're currently working through our list of good first issues. If you have ideas, if you want to help, if you're interested, definitely come talk to us. There may be a perception that OSL is harder to contribute to than other libraries because it's meant to be integrated with production renderers. You don't necessarily need to have a production renderer to work on OSL. Test Shade and Test Render are part of the project. They're self-contained, and they're actually really good proving grounds for features. And it's possible to write tests with those, and yeah, just generally interact with the library without needing to have a renderer to work on as well. You can register at this link here. You can just Google ASWF Dev Days to find the page. One thing I will mention, if you work for a company and you haven't signed our CLA, it might be a good idea to start that process now. Sometimes it can take larger companies time to get that signed. Also, if you're interested in contributing, make sure you can build the library that'll just help you hit the ground running if you really actually intend to work on code. So how to get involved? Our TSC meetings are every other Thursday at 2 p.m. Pacific time. I put the link for the calendar here. It can be found on the ASWF webpage as well. Our Slack channel with shading language on the Academy Software Foundation Slack, and of course, GitHub. And that concludes my portion of the talk. I'm going to hand it over to Mitch, who's going to give us a lightning intro to writing OSL shaders. And Mitch,
Okay.
I'll pull up your slides. Just give me 1 second.
Let me try and
try again?
Okay. Just gonna give it one more shot. I'll see what happens here.
Okay.
Share. Working?
It is working. Amazing.
Oh, miracle of miracles. Yeah.
All right, take it away.
Okay, good deal. All right, so yeah, like Chris said, everything Chris talked about was like, OSL, how it's built, how it's integrated with renderers and things. But the purpose of all that is so that you can write shaders in open shading language. So that's what I'm going to talk about, is programming OSL shaders. Okay, so if you're unfamiliar with shading, I have no idea who the audience is here. So I'll just start with the basics. So it refers to the computation of the surface characteristics on objects or volumes or lights, and how those interact with each other through closures and things like that. So for a little bit of history, the idea of a programmable shading language was first proposed by Rob Cook in 1984. And the first formal spec and implementation of a shading language was done jointly by Pat Hanrahan and Jim Lawson. Their efforts became the RenderMan shading language that was described in the RenderMan interface spec at the end of the 80s. And you can see in blue here, a significant portion of that spec was devoted to the shading language itself. So that's just highlighting the importance of programmable shaders to the rendering process. That spec was the forerunner, the RenderMan interface spec was the forerunner of USD. Well, USD itself doesn't contain a shading language, but it concerns itself with associating externally defined shaders with, and their variants with, objects in a scene. OSL is like most shading languages. It was a direct descendant of the renderman shading language. And all modern shading languages basically trace their ancestry back to the work of Hanrahan and Lawson. And yeah, so Chris mentioned OSL code repository and tools can be found under the Academy Software Foundation's GitHub account. And again, Chris mentioned some of these. If your interest is in helping to develop or maintain OSL or to incorporate it into a software system, such as a renderer, you'll want to join the SWF Slack channel for OSL and the OSL developers mailing list. These will require you to create an account with the Linux Foundation since they manage the SWF projects. So, however, as I'm saying, if we're writing OSL shaders is where your interest lies, then within the OSL GitHub repository is the open shading language spec in this PDF file, and which will, or is now, as Chris mentioned, on read the docs URL. Anyway, those contain a complete description of the shading language, and that's your primary resource for the OSL reference when you're programming in OSL. So to write and use OSL shaders, you need a system that incorporates it. So I'll quickly show you a few. Here, Appleseed is a renderer and an application plugin ecosystem. The applications are used to generate the scene and attach shaders to objects, and then the renderer uses that scene description and the associated shaders to produce an image. There's also the Cycles renderer, which is part of the Blender project. And then there are some commercial systems such as RenderMan and 3Delight and Autodesk Arnold. Octane Render is an interesting one. It's a GPU only renderer. So you'll need an NVIDIA GPU that can run Kulla. So now for writing OSL shaders. So I'm only going to talk about pattern shaders. I'm not going to talk about defining closures and other responses. This is just generating patterns. So to generate these surface variations, you need to know where you are on the surface, plus some other information about it, such as its orientation with the incoming light direction. So these are the predefined or OSL global variables that contain that information. So here's our first pattern shader. It shows how P varies over the surface. The source code for an OSL shader is contained in a text file with a .osl extension, and it's compiled with the OSLC compiler to produce a .oso output file. It's this .oso output file that a renderer or other application uses. The shader starts with a declaration of its type and name, which in this case are shader and global underscore P. In parentheses are the shader's parameter declarations. Parameters are how individual shaders are connected to each other in order to create a larger shading network. In this shader, there's only a single output parameter of type color, which is named P underscore color. Its default value is 000. Then next comes the body of the shader code in curly brackets. And in this shader, we start by declaring a point variable named P underscore object. Then we access the global variable P within the OSL transform function. To access an OSL global variable, you simply use it. P contains, as I mentioned, the three-dimensional location on the surface of the object that's currently being shaded. Common space is a coordinate system used internally by the renderer for its own computations. So common space could be any space or any coordinate system at all. So to convert a variable into a known space, it must first be transformed out of common space and into object space in this case, which is the coordinate system that the object being shaded was defined in. In this image, P object's values are ramped in a sawtooth pattern by subtracting the floor or integer portion of the point's values from itself. And this floor function operates on each component separately. N and NG are surface normals. These are unit length vectors that describe the surface's orientation. N is simply called, typically called the shading normal, and NG is the geometric surface normal. I is the I vector, as in the vector pointing from the observer, or I, which in this image is the camera, to the surface. U and V come from the geometry itself and contain its inherent two-dimensional surface parameterization. Here you can see that each subdivision face of the teapot has its own set of geometric UV coordinates. So I talked a bit about OSL coordinate systems when transforming global variables from common space into object space, but there are a few other useful spaces available in OSL. Excuse me, this generic shader is used to generate the images in the next slides. It has an input string space parameter and one output parameter. The transform function is used to transform a common space P value into the chosen coordinate space, and then the shader generates a sawtooth color pattern from it. So as I mentioned, common space is arbitrary, it's undefined. Object space is relative to each individual object in a scene. So any transforms that are applied to the object are also applied to the object's object space. In this case, the teapot has been scaled up in size relative to the reference cube and spheres in this scene and has been rotated and translated. The background object has also been scaled up, so its variations are quite large. World space is the scene coordinate system. It's rigid and uniform throughout the entire scene. So as objects are moved throughout the scene, they will swim through the object space. Camera space represents the three-dimensional transformation applied to the camera that's used to view the scene. So as the camera moves, this space will move through the scene and all the objects within it. Screen space is relative to the camera's image plane. It's two-dimensional and its origin is at the center of the camera's view. NDC stands for normalized device coordinates, and it represents a 0 to 1 range coordinate system that describes the output image rectangle. And then we have raster space. This is the two-dimensional pixel coordinate system. So each pixel is one unit in raster space. In contrast to pattern generation, conversion shader doesn't generate a varying pattern, but is instead used to convert one set of parameter values into another. This one just converts a set of float values into a color. When this shader is compiled and used in a content creation application, it will appear as a shading node, as shown at the bottom, that can be used in a graph of shading nodes, which are interconnected by their input and output parameters. Its input parameters are also presented, as shown on the top, in a user interface where you can set their values directly. This shader does the opposite of the previous example. Note that the struct-like notation for the color parameter is being used to access its separate R, G, and B components. You'll also note that this shader has more than one output parameter. The fact is, a shader doesn't need any input parameters at all, but it must have at least one output parameter. Otherwise, it's not going to be connectable to anything and therefore won't be of any use. This shader takes a base color and metallic value and converts them to diffuse and specular response colors. This has been around for many, many years, but in this implementation, the control parameters, which are shown in the middle section of the parameter declaration section, are exposed to the user so they can have the ultimate and control to fine-tune the results. The OSL mix function just linearly interpolates between the first two arguments based on the third control argument's value, as it ranges between 0 and 1. Here it is creating semi-metallic blue material. Note the shader's outputs are connected to the diffuse color and specular face and edge color parameters of a surface response shader. And now for some pattern generation, which is one of the most important uses of programmable shaders. For that purpose, OSL contains a noise function that can generate various randomized patterns. This shader starts with a point type space input parameter, which can contain a varying surface quantity, something similar to the OSL global variable P, but perhaps scaled or otherwise transformed in some way. The size parameter adjusts the size of the resulting pattern. A bigger size value produces bigger pattern variations and vice versa. The type parameter determines the specific type of noise that is going to be produced. And shown here is a noise of type cell, which isn't really a noise, but is a uniform random value. It produces a constant result based on the integer portion of the arguments to noise. It's often used to generate a constant value based on an object's ID in order to ensure that no two objects have the exact same appearance. Perlin noise is named after Ken Perlin. U Perlin in OSL means the result of noise is unsigned, so it ranges between 0 and 1 rather than -1 to +1. Variation provides a fourth dimension to the pattern, and you can use it to animate the result or ensure the pattern is different on different objects. Simplex noise was also created by Ken Perlin. It is simpler to compute as visually isotropic and has higher contrast than does Perlin noise. Gabor noise is named after Dennis Gabor. Its result is based on a filter that's applied to an underlying pattern. Note that its output ranges from -1 to +1, as there is no unsigned Gabor noise type. And so now we'll use noise to generate a fractal pattern. This type of pattern often appears in nature, so fractals are a very useful capability. The classic fractal control parameters are dimension and lacunarity. To these, I've added erosion, which is used to smooth either the low valued areas or high valued areas of the result, and iterations, which directly controls the number of times the base pattern, in this case a noise, is combined with itself. And if a shader begins with the same pattern generation space used in the noise examples, we then initialize the fractal generation variables, beginning with the frequency of the initial pattern, which is set to 1. Then a for loop is used to accumulate patterns of different frequencies and magnitudes into the result. The first two lines produce the current iteration's noise value. Then the frequency and sum are updated for the next iteration. As you can see, lacunarity scales the frequency of each successive iteration. Erosion applies an offset to the magnitude by examining the currently accumulated result. High-valued areas will have the erosion parameter added to their frequency exponent, and low-valued areas will have the erosion value subtracted from it. Finally, the magnitude of the next iteration is computed using the classic fractal equation. And then once all these iterations have been accumulated, the result is normalized, so it ranges between 0 and 1. Using the red channel as a displacement height, you can see how the erosion control works. Negative erosion causes the lower valued areas to become smoother, and when erosion is positive, the higher valued areas are smoother. These examples use simplex noise on the left and cell noise on the right. And finally, rather than noise, a Voronoi pattern is being used on the left, and a texture map is being used on the right. This illustrates the fact that it's possible to use any fundamental pattern and create a fractal from it. To conclude, I'd like to point out that LAIKA is committed to open source software and has a number of open source repositories on GitHub, one of which contains these and other OSL shaders. I'm also presenting a full 3-hour course of this material at SIGGRAPH, which will cover all sorts of pattern generation techniques commonly used in computer graphics. And you're among the first to know that I've also written a book that covers all the material from the SIGGRAPH course and much, much more in far greater detail with many more examples. I want to note also that while OSL code in general, and especially these examples and those in the book were developed using RenderMan, the shading techniques apply to any rendering system. It's also worth mentioning that OSL source code is pretty easily translated into other shading languages such as GLSL without too much effort due to the similarity of all such languages. And that's it for me.
All right, thanks, Mitch. Gonna bring back the original
Stop
slides.
share. Stop share. There we go.
Oops. Okay. back to my slides. And now we have a presentation from Akshay and Fran from Pixar. They've actually recorded their talk, so I'm gonna play it here. But if you have any questions for them later, just drop them in the Q&A.
Hi everyone. Today we're excited to talk about the use of OSL in XPU. My name is Akshay Shah. I'm a senior software engineer in the Renderman group here at Pixar, and I'll be presenting with my colleague Fran Gonzalez, also a senior software engineer in the Renderman group. Okay, so we'll be talking about three parts where OSL is used in XPU: material closures, sample filters, and display filters. So Renderman XPU fully embraces open shading language that artists can use to expand the capabilities of the renderer to create their creative and artistic vision without any limits. Before we dive deep into it, let me start by setting up some context and background about how and where OSL comes into the picture for us. Keep in mind, this is a very high-level overview for very complex design that makes Renderman XPU the way it is. There are other places we use OSL, for example, displacement, and we will not be talking about that part of the code in this presentation. Okay, so like many path tracers, we start off simple by generating camera rays and doing direct lighting, and followed by intersection routines and then shading. In this section is where material closures are used. Pattern shaders are plugged into a pattern network graph, and that can be plugged into material closures, where then PXDFs can evaluate and sample based on material descriptions. Followed by that, once we exit out of the ray tracing loop, we come over to post-processing and we run OSL sample filters. I'll go more into detail about what these are in just a bit. Once we are done evaluating sample filters, we come over and accumulate all sample results into the global frame buffer. Display filters are immediately followed up by this step and act as a post-processing imager shader close to the renderer before dispatching them to the frame buffer. The frame buffer then goes over to the display clients. These could be writing down to disk like an OpenEXR file or any form of interactive viewer. Okay, by definition, what is a closure, material closure? A closure is an expression along with all necessary contextual data, for example, its parameters. OSL defines 4 different types of material closures: surface closures, volumetric closures, light emission closures, and layering and signaling closures. In XPU materials, BXDFs are implemented as plugins to allow for easy expansion of the shading capabilities of the renderer. BXDF kernels that allow computing their evaluation or sampling are executed on both the CPU and GPU device, sharing most of the code. For XPU to support material closures, several important architectural changes need to happen. First, for each existing material or BXDF in XPU, we need to create our own custom material closure. Second, we also needed an efficient way to allocate all the closures and their corresponding DAGs they create at runtime. With those 2 elements, we could drive the evaluation and sampling of BXDFs by the mentioned material closures. Here we've listed some of the examples of material descriptions: Pixar Surface, Pixar Disney BSDF, and some other material X Llama ones as well. Okay, moving on to sample filters. Sample filters are plugins that describe color transformations made to sample values before they're pixel filtered. What this means is sample filters always operate on raw camera samples once they change a sample in the frame buffer, the value will stick on in the final rendered image. In XPU, they are implemented in OSL through the use of debug closure, texture calls, and a bunch of other OSL functions. So what is the domain of sample filters? For pattern shaders, the domain is the shading points, the shading hits we get on objects or geometry. For sample filters is the samples that are shot into the raster via the camera. So each sample in a pixel is a shading point. The basic functionality of it is we read sample value at the current pixel location via texture call, modify the sample and write the result back via a debug call. Now, the good thing about sample filters is that since they operate at a sample level, you can access hit information like normals, hit instances, and different things. You can also call OSL trace to gather more contextual information about the scene. And lastly, display filters are plugins that define color transformations that pixel values get affected after pixel filtering. So once the accumulation of samples has happened into the frame buffer, we have raw pixels, and these raw pixels are what display filters operate on. So the domain remains very similar to sample filters, and that we are operating on each individual pixel. So think of it like a compositing plugin for your rendered image. The basic functionality remains the same. You read the sample values via texture and write it back via a debug call. So the only difference between the sample filter and display filter is that display filters don't get extra hit information, and we only are allowed to do pixel value manipulation. Okay, so why did we switch from C++ plugins, which our previous renderer, RIS, has already been using? Why the need for OSL? Well, that's a good question. There's a couple of things. One of them being that there's a large setup structure for the C++ plugin. Two, since XPU needs to work on multiple hardware, that poses a difficult problem for C++ plugins. There is low flexibility to move the same code over to the device. Currently, we support NVIDIA cards for the GPU, and the shader authors would have to write CUDA code or translate their C++ plugins into CUDA as well for it to run on the GPU. To avoid all that, just hand it off to OSL. OSL will do the necessary translation, and underneath the renderer will make all the right calls on the device. Another benefit of OSL, I'll demonstrate in a second, is chaining these filters is somewhat limited with C++ plugins. This here is an example of our previous renderer RIS being used to chain display filters one after the other. As you can see, only display filters are pluggable to each other, and they go into a display filter combiner before going off to the display driver. However, OSL has no such restriction. We can combine and create pattern network graphs that are pattern shaders, but plug them into display filters and together chain them in a linear fashion. For example, Pixar texture can be plugged in to drive the background color of a background display filter, for example. So it has added benefits to splitting up and visualizing these plugins as they should be shading nodes. Okay, so this means that it is clear that XPU we have embraced OSL and those three mentioned features demonstrated, but what technical challenges did we face and how did we overcome them? For this, I'm going to hand it off to my colleague Fran, and he'll help you get down the nitty-gritties of things.
Thank you, Akshay. So as Akshay mentioned, my name is Fran Gonzalez. I'm a senior software engineer in the renderment team at Pixar as well. And in the second part of the presentation, I would like to dive into some more technical details on how we proceeded to basically support OSL in the different stages of our render that Akshay mentioned before in his part of the presentation, and also the technical challenges that we encountered and how we overcame them. So first of all, to be able to support closures, both mature and debug closures in this case, we needed an efficient way to allocate and free the memory to store those closures. And that efficient way to support closures was supposed to happen in a quite complex environment where several threads were going to process many shading points at the same time, with many closures per shading point being allocated at the same time as well. In addition, handling closures and their persistency in time in a complex production integrator like Pixar path tracer can be quite a complex task. Basically, the evaluation of shading networks for different purposes could happen, for instance, opacity or BXF evaluation, and those evaluations could be intertwined, making it quite difficult to manage all the closure data generated in an efficient way without, for instance, overriding existing information. And last but not least, let me remind you that in OSL, currently there are a few differences, important differences with respect to the CPU and GPU implementations regarding how the memory related to those closures is managed. On one side, for CPU devices, OSL already handles the memory allocation by using a closure pool, which is great. But in this case, there's one big caveat for us. Once a current shading point or batch of shading points are processed, the memory used to allocate all its related closure data is going to be freed and reused by OSL for the next shading point or batch of shading points. And as you can imagine, this imposes serious problems with respect to the persistency of that closure data, which might be needed later on by integrators. And on the other side, for GPU devices, currently there's no reference implementation that exists in OSL. And as a consequence, we needed to implement our own corresponding way of handling that data. And OSL at least provides an API, a set of methods that we can implement as engineers to provide our own GPU closure pool. So what was our solution to be able to support closures in different devices for XPU, which is a hybrid render, and as a consequence support material and debug closures? So exactly, we implemented our own closure pool, which is no other than a memory pool where information from material or debug closures, depending the situation, is going to be stored. So let me dive into some more technical details on how we proceeded in XPU to implement that closure pool. First of all, I'm going to talk about the memory requirements, and then I will show you some examples on how we use that pool to, for instance, evaluate and sample BXDF or execute display and sample filters. So the data that we store per shading point in this case is no other than the closures a shading point needs to process, plus the DAC of closures for that specific shading point. So later on, we're going to be able to reproduce the right result in the way it was intended. So in the right order, basically. As an example here, we have a shading network of materials using closures in where we have a layering between a llama dielectric and a llama conductor, and then we apply that material on the front face of a surface using llama surface, the llama surface node. In this case, we would only store the four closures: the llama dielectric, the conductor, the layer, and the surface closure, and also that specific DAC for that specific shading point, so we can later on reconstruct this specific material in the way it was intended to be created and displayed. Then let me talk about the memory requirements of our pool. So first of all, we resize the closure pool up front with enough memory to handle n number of nodes or closures per shading point. Let me mention that in the case of material closures, after scene ingestion and before the render process starts, we know the maximum number, we already know the maximum number of closures we will need. But for the debug closures used for sample filters, we don't know the maximum number of closures, which is the number of debug closures calls that we would encounter in our shaders from our shading networks. Which means that in that specific case, we could need to resize the closure pool to accommodate all the debug closures calls once the shaders containing that call have been executed at least once. So now that we know the data that we're going to store in the closure pool, let me also talk about the other issue I mentioned before, which is related to the persistency of the closure data in the closure pool and how we solved it. So as I mentioned, to be able to accommodate all the situations of a complex integrator where shading networks evaluations are executed and intertwined for different purposes, we needed to come up with a solution that was, first of all, performant. For instance, avoiding continuous resizing of the closure pool, and two, simple enough. In our case, we opted for a double closure pool implementation. As they say, when you cannot win with just one, just use another closure pool and that's enough. But jokes aside, in this case, using this dual approach of closure pools allow us to easily have two differentiating networks storing their closure data info at the same time and with a potential different lifespan without overwriting information that is supposed to be needed later on by the integrator. And finally, after describing what we saw in the closure pool and how we overcame the persistency issue, let me finally illustrate how our materials are evaluated and sampled and how displays and sample filters work. So first of all, we start executing our shading networks in the case of material sampling and evaluation, and store the corresponding closure and DAG for each shading point. Then what we do is we sort all the shading points in a batch by the patterns and BXDFs or materials, and we start traversing the DAG of closures coherently as it will be the same for all shading points within the same bin, given the fact that we have previously sorted that bin, that set of or batch of shading points by pattern and by BXDF. In this specific case, we would start by the llama dielectric node, then we would evaluate or sample the llama conductor, execute the layering between both, and last but not least, the llama surface, and we would consider this shading network fully evaluated or sampled. And similar to the material closures, sample and display filters are evaluated via this process closure loop. Sample filter, DAG, and display filter DAGs are stored in the closure pool, and calls like texture or gate attribute, for instance, can be evaluated at runtime. Finally, processing the closures will let the renderer know that this color or float value needs to be written down to disk. And last but not least, as a conclusions, and talking a bit more about what's next for RenderMan XPU related to OSL. Let me be clear. For us, for RenderMan XPU, OSL will continue to play a key role as a key part of the renderer. And all the work that has been done and is being done in RenderMan XPU with respect to material closures will definitely pave the way to material X support in RenderMan XPU, which in fact is a collaboration that we just started with Lucasfilm and ILM, and also future support for OpenPBR through the Material X support in RenderMan XPU. So that's all for us today. Thank you very much for listening, and if you have any questions, we're going to be happy to answer them. Thank you.
Hi everyone. Today we're
Okay, we're back. So that concludes our program for today. We actually went slightly over time, but we have a few minutes for questions. If people have any, just drop them in the Q&A box and be happy to answer them. Since I don't see any right this minute, maybe I'll start by asking one for Fran and Akshay. You mentioned llama closures in your talk. I'm curious if you can talk to the difference between the llama closures and some of the standard Material X closures, and if you see those kind of like converging at some point, or how you think they'll evolve going forward.
Yeah, so I can take that one. So basically, the main difference is that Material X llama closures are custom-made closures, like the ones that we create for Pixar surface, which doesn't have a public closure. So we created our own custom closure for for that specific BXDF. But besides that, besides creating the closure, like another built-in closure within OSL, they behave exactly the same as any other material closure in OSL. So the difference is that they have different parameters, and they are expected to produce like a different results. In this case, it's a result that we implemented ourselves, our own custom implementation of Pixar surface. And the same for Disney BSDF and other in-house materials that we have at Pixar.
Makes sense. Makes sense.
Thank you.
Okay. I don't see any other immediate questions. I'll just mention, as you see on the slide here, we have a few other virtual town halls from the ASWF. There was some GLX one this morning. In case you missed it, it'll be uploaded to YouTube a little bit later. OpenImage.io, which is a dependency of OSL, will have their virtual town hall tomorrow, as well as OpenColor.io. These are all related to open shading language. Also, like Mitch said, he's going to be giving a whole SIGGRAPH course on OSL on Thursday at SIGGRAPH. And if for those of you attending DigiPro, I'll call your attention to the presentation from Imageworks about porting their production renderer to the GPU, and I'll include some descriptions of the challenges they had with running OSL on the GPU there. So with that, I'll conclude today's session, and thank you very much for attending. And please join us on Slack if you have any more questions and want to get involved. Bye.